Hello, welcome back. Okay, so we left yesterday after we discussed this. What is a set? How can we represent it with a Venn diagram? Venn diagram. Right. Now today we're going to see some very important concepts of like there's a little bit advanced and little bit abstract concepts that I'd like to show you today. So please bear with me and try to think of it. I'll be giving visual demonstrations as well, so we understand it alongside. So let's look into this first example. Given C is a subset of this particular set, and C union C complement is the whole set itself, and this is obvious. So let's assume something like this. Let's assume that this is this curly C, right? That this set, and within that there's a subset which looks something like this. Let me just do something. Just a second. Focus. All right. Okay. So this is a subset which we are going to call the C that you see. This one, right? This is the C that you are seeing. So what is left out of it? It's the all remaining portions. Right. This would be this blue section. The purple one is C. So the left everything else would be C complement. C complement, right? So it makes sense that if our whole population is this C set itself, then C union C complement would be the whole C set, right? Please understand that the right to the power C, that is very exactly same as this hat that I'm doing, C hat. It is exactly the same like that. Okay, and then C intersection C complement would always be null, null, whole set, and the final what is it? C complement complement. Okay, so complement of this, complement of, how do I mark it? Yeah, complement of this thing, it is going to be this only, right? It is going to be this only. We understand that. So essentially C complement and complement of it would always be C. So let's say, how do I say? You have 3 rupees, I have 7 rupees, and altogether total we have 10 rupees. Now your complement would be my amount, and my complement would be your amount, right? So if both of us altogether has 10 rupees and I have 3 rupees, then what is the complement of that? Like, what, how much do you have? You would have 7, right? Exactly. It's similar like that. The sets are very similar. I may be over explaining a little bit, but let's dive into De Morgan's law. It's again a very trivial understanding of sets. So I'll just write it down. The first law, let it is C1 complement C2 whole complement is equals to C1 complement union C2 complement. Now we'll try to look into in terms of this Venn diagram only. We won't elaborate it much further than that. Imagine, now earlier you remember this was our C. Now understand this whole rectangle, it is our whole set. Okay, and C1 and C2 are two subsets out in the subsets. I'm just writing it, I'm just drawing it as a circle. Don't fall for it. It might be of any shape or it's abstract thing. This one is C2, sorry, C1, and this one is C2. C1 intersections C2 would be what? It would be this portion, right? And what would be the complement of it? It would be everything else. This whole whole space. Anything except for the blue part. Right? This we have drawn from this. Sorry. This we have drawn from this. Now let's start again a similar drawing. Now we'll try to check what it looks like for the other part. For this one. Now again this is C1, this is C2, and this whole set itself is C, the whole set itself. Don't worry about it much. Now what is C1 complement? Now C1 complement is everything which I'm going to draw in green. Next C1 is this, so everything outside of it is C1 complement, right? Whatever is here, the whole space. And what is going to be C2 complement? C2 is this one, right? This one is the C2. This one is C2. So what you'll see is C2 complement would something like everything out. Maybe I use a different color. The green is super. Yeah. So we take everything outside of C2. I'm really sorry because C1 and C2 both are essentially going away. Now you see, the only part that is left here is this, the middle part. So middle part is not included anywhere from this. So anything except for this middle black part is of this, which is exactly similar to this other graph that we drew, right? So this we both represent same thing, right? These both represent the same area, if you can imagine. Great. And similarly, we can look into the other way. Now, I'm not going to draw this extensively, but I want you to imagine a little bit for yourself as well. A second one is exactly opposite of it. C1 intersection C2 complement equals to C1 complement intersection. Sorry, I'm really sorry. It's union. C1 union C2 complement is equal to C1 complement intersection. Is that what we did earlier as well? No. My bad. Nevertheless, it's exactly same, so I sometimes get confused. Not same, but very similar. So let us just draw the first one first. This is C1, and then why am I drawing so bad? Let's imagine this is C1. Let's imagine this is C2. This is C1. This is C2. This is whole set C. Now C1 union C2 would be what? C1 union C2 would be I'll just I won't draw the whole thing. C1 union C2 would be this whole space, right? Then what would be remaining per portion? that would be the complement we have to take, right? The complement would be this part. And for C1 complement is what? C1 complement is this whole space, right? Similarly, C2 complement would be what? C2 complement would be this whole space. Now notice we have to take intersection of both of them, and this space is not covered by C1 complement, right? This C1 complement does not cover that part. C2 complement does not cover this part. So anything except for this, and obviously this is what we have, correct? C1 union C2 complement. Yeah, that makes sense. So now it would be, let's just draw it in some other color. Yeah, it would be this blue, which is exactly same. Now one can prove it in a more conventional way. I'd I'd refrain from doing so. It's all right. These are very trivial ones. To understand how the sets work, we have to understand them first. All right. This works. Okay. Now let's move on to this example. Okay. So let's C be a set in two-dimensional space, and let QC be the area of C. What is QC? QC is a function, set function. Okay. So what does a function do? Is essentially it takes a value. So let's say we have a set. Base set. The set can be anything, correct? And then imagine it goes through a function or some kind of device or some kind of processing function. For example, you know how crops turned into wheat, right? There's a machine which, so wind, it's not called windmill. I think it's called a mill of some sort. I'm not too sure, but essentially that mill essentially takes the um, raw materials and then turns into the wheat that from which we make breads, roti, all of these things, right? So essentially, a function is like that. A function is like a mill or something of that sort, which converts a particular set to another set or outputs to another set. This will be output. This will be input, right? So QC, the QC you see here, is one such function. So what it says that QC be the area of C if area of C is a two-dimensional space. It's on two-dimensional space, and it has a finite area. If it has a finite area, then it would be the area itself. Otherwise, QC be undefined. That's all right. So let's understand the function first. QC, it is coming from uh, the real space, like two-dimensional space, right? And it is outputting. You see this this QC is essentially this R2 is this, and essentially R is this, nothing else, right? So what is happening is essentially, you imagine a 2D area. I'm very bad. I'm using I was using Venn diagram, so I drew that. This is the y-axis. This is the x-axis. So let's imagine anything. Uh, uh, Whatever the coordinates can be anywhere, but let's just assume that it's 1 unit, 1 unit, 1 unit, 1 unit. It's a square, even though it looks like a rectangle. Then when we apply, this is the set C, right? Any set C. So when you apply QC, this function on top of this, it will generate the area out of this. So we know area of a square. Area of square is I forgot, a square. It is called a square. Yeah, 1 into 1. Essentially the side, right? Equals to 1. So it would be 1. So for this particular one, it would be 1. Now, C, they have defined x square plus y square less than or equals to 1. Okay, how does it look then? Um, Let us draw that particular 90 degrees and not 90 degrees anymore. X, y, 0, 1, 1, right? X square plus y square is less than equals to 1. So it will be a circle. Now, why is this a circle? I think this is a class 10 question probably, but I won't dive into that much basics. But I believe whoever is watching this already knows that this is x square plus y square is a circle. Class 11 probably. Nevertheless, so how it looks is, so area of this would be 1. So this radius is 1, and we know circles um, area is pi r square. This is r. Now here r equals to 1, so it would be pi r into 1 square equals to pi. So that's what they are mentioning here as well. That then QC would be pi, right? If C is this, then QC is 0. Now you have to understand these are just three separate points. Now if you look into this, I'm writing that one, x, y, 0, 0, 0, 0, 0, 1, 1, and 0, 1. I am really sorry. Yeah, 0, 0, and let's say this is 1, 1, 1, and then 0, 1. These 3 points. Now these 3 points itself doesn't make anything. It does not qualify as an area. These are just 3 points. So it itself wouldn't have any area, so it is undefined. I'm not too sure why it is 0. It should be undefined, like that's let QC be undefined. So it should be undefined unless I'm getting something wrong, maybe not. Let's trust the authors. No, I don't think you should trust the authors. It should be not. Nevertheless, you get the point why it is written like that. And the last one would be cxy, wherever x is less than 0, y is also, sorry, x is greater than 0, y is also greater than 0, greater than equals to, and x plus y less than equals to 1. Now this is also a pretty straightforward case. So we have to consider only this is 0, 0. Earlier did I write only 0? I'm really sorry. 0 is the 0 vector. Let's imagine that. Yeah, 0, 0. Okay. Then x greater than 0. So we only consider this portion for x greater than 0. For y greater than 0, we only consider this portion, which was on the right side of this. Correct? Okay, and then x plus y less than 1. So imagine this is um 0 1, and this is 1 0. So a line like this. So you see we have a area now which is somewhat this portion, right? Now uh, two ways one can calculate it. It's a half of a square, it's a 90-degree triangle. I'm really sorry, I was not English medium guy, but yeah. Okay, so this would be essentially half of the square, which is essentially half into 1 square equals to half. So that would be QC would be half. This makes sense. Okay, let's move on. I think I'm spending a little much time more to go through these examples, but I think these examples should help you understand what's happening. We'll be covering a lot today, so let's see. Let C be a set in one-dimensional space and QC equals to sum of functions. Okay, and the function is whenever it's an integer, it's 1 by 2 whole to the power x and 0 otherwise, right? Okay, then if C is on this space, so what is okay? So example, yeah. So if C is x 0 x less than 3 or not equals to strictly greater than 0 and strictly less than C. So what are the integers in between them? For the fx we see it only takes the integers. So the integers would be 1 and 2, right? Oh, these are equalities. What am I seeing? Yeah, 1 2 3 would be here. Okay, then QC would be sum of all of them, right? This function we apply, sum of C f of x equals to 1 by 2 plus 1 by 2 square plus 1 by 2 cube, which comes out to be 7 by 8, which is written here. Okay. Okay, let C be a one-dimensional set. Let QC equals to the exponential function, the inverse exponential function. And this, if C is less than 0 to infinity, the integral of this is 1. 1 to 2, then we can calculate this value. If C is 0 to 1, then we can only okay, C1 and C2 is this 1 2 3, so greater than, then even then we have 0 to 3 only. Union would be essentially just that, right? Yeah. Now you have to see, when we're integrating and unioning the space, we are taking the union of the range of x, right? Range of x. We are including both of the ranges, 1 to 0 to 1 and 1 to 3. That is why this calculation is happening, which is exactly same. Like that's what they're showing. Okay, and let C be an n-dimensional space, and let this be an integral of multiple huge integral. Okay, x1 x2, all of them are okay, they're increasing and all of them are bound within 0 and 1. This is a very funny one, not a funny one, but these are very cool ones. So what would be QC here? Sorry, I'm just overwriting on top of something. Yeah, QC is integration of 0 to 1, 0 to xn, 0 to xn minus 1, 0 to x3, 0 to x2, dx1, dx2. Now, when you consider this, what is this would become x1 bound by 0 and x2, right? So this would be essentially x2 itself. This would become x2, 0 to x3. I'm writing x square somehow. And then it would have dx2, dx3, and so on. And this would all have integrals 0 to 1. And this would become x2 square by 2. Now x2 square by 2 would be x3 square by 2, essentially. x3 x3 square by 2. Okay, it will just keep on increasing one by one, right? So slowly it will become from there it will become x7 square, sorry, x7 to the power 6 divided by 6 into 5 into, sorry, 4 into 3 into 1, correct? So essentially it's just going to increase. So at the end it would be integral of 0 to 1 xn to the power n minus 1 dxn by n minus 1 factorial, if I'm not wrong. Yeah. Now ultimately this would essentially turn into 0 to 1, and that would be 1 by n factorial, because x into the power n minus 1 would be becoming x to the power like it will, by n it would come to the power n, and 1 to the power n minus 0 to the power n, so that would become just 1. So it will be 1 by n to the power 1 as 1 by n factorial. So it seems correct. All right. Now here we see another there is a couple of exercises here which are pretty intuitive and easy if you do go on with the functional approach, or as well as the Venn diagram approach itself. If it's possible to do it with Venn diagram, I'd say go ahead with it because it's the easiest one. But otherwise you were welcome to try out the functional methods. It's very straightforward, but please do let me know if you have some questions. Now, okay. Let's look into this. By use of Venn diagrams, in which the space C is the set of points enclosed by a rectangle containing the circles C1, C2, C3, compare the following sets. These laws are called the distributive laws. Okay, so an intersection C2 union C3. Okay, we'd use a Venn diagram because that's the easiest thing. Let us draw three let this be C1, C2, C3. Okay. C2 union C3. Okay, C2 union C3 would be this whole space, right? And C1 intersection C2 union C3 would be this space. Correct? Yes. So from one approach, we see it is this space. Okay. And okay, let's look into the other one. C1 intersection C2. C1 intersection C2 is this part, which somehow is not visible. I should have used a different color back then. I think green works fine. This is from the first one. Yeah, and then the second one, C1 union C2. It is this portion, the heavily highlighted one, correct? And then C1 intersection C3. C1 is this portion, right? So you see, union of both of them would be the exact same space or same place itself. Which means that it's equal. All right. Let us draw again on top of this only. I just don't want to draw another. Yeah, okay. Looking at the second one. C1 union C2 intersection C3. Okay, let's just find out what C2 intersection C3 is. C2 intersection C3 is essentially this portion, right? And if we union C1 inside this, then it would become this whole space, right? Okay. And then there would be C1, and then we're looking into this one now. C1 union C2. Okay, this is a huge space. C1 union C2. Right, this is a space, and we have to find the intersection. Okay, I forgot to write it down. Maybe just write it down what space it was earlier. Yeah, this left one was this space, the green marked one. Now let's look into this one, intersection with C1. Okay, C1 union C2 is this whole space, right? And C1 union C3 is this space. So you're seeing the same story is happening. There's an intersection in between these two spaces. The C1 part is always there, and the common part between C2 and C3. Essentially, that we have what we have drawn already. But that is the exact same space. Okay, these both are truths. And remember, these are called distributive laws. So essentially, how you can imagine is C1 is getting inserted in between this space, and whatever is the sign in between them, it is going to apply. It will do this one first, which is nothing but this, and union of this intersection with this part. So essentially that. Similarly, the other way is true. You can figure it out, no worries. Now we're coming to the little bit interesting parts. Slowly now it is going to be more challengingly interesting, I guess. Okay, I'm not too sure. You guys are pretty smart, so. Probability is definition. What is the definition of probability? Okay, I won't write it down. I'd read through it first, and I'll explain some of it. So C be the sample space, and B be the set of events. Okay, B is the exhaustive set of like events, right? And P be the real valued function defined on B, and then P is a probability set function if it satisfies the following conditions. Okay. So the probability function is something similar to the set function. You remember the q functions like this. Now instead of q, it would be probability of something, probability of a set. Um, so C be the sample space on which we are set of events. Let be the set of events, and essentially, let's assume this is some sort of events, and P is the function. This is the probability function, and it outputs a value which is in real numbers. So there are certain like certain criteria on top of it. So essentially, this criteria number one would be that probability of any event of a set of all events is essentially going to be greater than equals to 0. So if we this is, let's imagine B is like this, right? B is like C1 event, C2 event, and so on. So probability of any event is going to be greater than equals to 0. I mean, it can happen that this particular event has probability 0 as well, but it has to be non-negative first of all, right? The what is going to be C, the second one. So it is a sample space. Essentially, imagine like these are events, like this is one event, this is another event in the notebook, and this is another event. The whole like there might be multiple other events, right? See other C's. The whole sample space is called the C. See, this curly C is essentially the sample space, right? So which is set of all possible events uh, that can happen together, somewhat not together. It's depends. So essentially, that sample space, the probability of the whole sample space has to be 1. Okay, that's what it means. So already we understand that this is always less than equals to 1, the probability of any event, as well as it is greater than equals to 0. Now if Cn is a sequence of events in B, and all of them are non like null, not matlab, they don't have any common intersection portion in between them, then union is equivalent to summation. Okay, let's imagine it like that. I'll just draw it right here, this space. Imagine this is C, this is event C1, event C2, event C3, C4, C5, C6. You see the just like here, you were able to see there is an intersection portion between C1 and C2. Similarly, an intersection portion was in between C2 and C3. But here they have told explicitly that they have no common, there is no intersection part. So essentially, all of them are not connected, like how it was here in this case. So in that case, you can understand union of all of them would be what? Union of all of them um, would be this space, right? This, it will cover this one, C4, so whatever it is. So you can already see that union is equivalent. The union is equivalent to the summation. That is what this thing is calling and saying, nothing else. Now, uh, this particular phenomena where it is mutually exclusive, it is called mutually exclusive. A pair is disjoint. That's what I was trying to say. That they are not connected; they are disjointed. Right? Then it is going to be called mutually exclusive collection. The C1 to C5, C1, C2, C3, C4, um, C5, C6. It would be. So C1 to C6 are in this case. In this case, it is always going to be um, mutually exclusive, right? And it is going to be said exhaustive if union of all of its events is the sample space altogether. I mean, and let's say that everything which is not here, which is outside the C1, C2, C3, C4, C5, C6, and by that I mean this space, the green portion only. Let's call it C6, sorry, C7, and the whole set is C. You can see that they are already disjointed. They don't have any common spaces. Like C7 does not include C1, C2. The blue portion it does not contain, right? The C7 part. And C1, C2, C3, C4, C5, they don't even have anything. So then it is called exhaustive because sum of all of them is the whole sample space C. The whole sample space C itself. Correct. Okay, which makes sense. Then summation of all of them would be 1, obviously. We can understand that because you have to understand the probability of this. You have to understand probability of this is going to be always 1, right? So this event is nothing like in the case above I was showing. C is nothing but C1 union C2 union C3 union C4 union C5 union C6 union C7, right? This event, so all of them are independent, so that is exactly, if we write probability of C, it would be probability of union I equals to 1 to 7 Ci, which is nothing but the summation of all of them, right? Which is nothing but summation of probability of Ci, I equals to 1 to 7, which is 1 because this is already 1, we know from here. And we can also see in the graph itself that probability of all of them combines together. So 1 altogether. Now the next part is also very intuitive. There's proofs written which we can do one way, another way also we can see. Let's say that this is C, the whole sample space is C. This is event C1. Let's say this is C1 complement, right? Everything else is C1 complement. So we already can see that probability of C1 equals to um, probability of C1 complement, one can say, equals to 1 minus probability of C1 complement equals to 1 minus, yeah, that is what the theorem was. Never mind. But yeah, also we can say like equals to probability of C equals to C1 union C1 complement, then probability of C, which we know is probability of C1 union C1 complement, which you know is equals to 1 already. That means from this we can get probability of C1 plus probability of C1 complement, which is 1. Essentially that's what this is saying, which is the desired result. We can just side it. Idea is very similar. Null set is 0. If the event has no space, it is a null event. then it is, the probability of it is 0 already. Also, C complement is a, let's take C, then C complement is the whole sample space itself, then probability of it would be 0 anyway. Now this is an interesting part. This means C1 is a subset of C2. Okay. Now, how do you visualize it? Let's understand that. Let's say this is C1. So C2 is something which completely captures C1 but might have more space as well, right? Which makes sense. So visually already saying, we can say that probability, because it has bigger space, C2 is always greater than equals to probability of C1. Visually you can already see. Proof is also very similar. So what it is saying is C2 is essentially C2 intersection C1 complement, right? C2 intersection C1 complement and union of, so essentially this portion, this part is this blue portion. This portion, and green is C1, right? There would be union C1, right? Then probability of C2 would be probability of C1. As they are mutually exclusive, they don't contain any portion together. Plus probability of C2 intersection C1 complement. Now we always know probability is non-negative, which is greater than 0. That means probability of C2 is always greater than equals to probability of C1. If we just remove this whole part, this is always get non-negative, right? So which is good. For each C, 0 less than equals to P of C. Okay, for any event, it has to lie within 0 and 1. We already know that the sum of all events is 1, and it has to be non-negative, so it is already proven. Like when we are defining the probability, I already told it is understandable. Okay. If C1 and C2 are events in C, then probability of C union of them is equals to this. Okay. Now this we can first of all see visually why it is, then we can go into the proof itself. C1, C2. What would be C1 union C2? Let me just draw this. This is C1 union C2, correct? Now, what is probability of C1? That would be this portion. What is probability of C2? That would be this portion. Now you can see already that this portion, if we just write probability of C1 union C2 equals to probability of C1 plus C2, this portion it gets calculated, like it gets counted twice. Intuitively we can, visually we can see. So one can easily write probability of C1 union C2 is always going. Remember the theorem, one might get confused already. That's why C1 plus C2 is probability C1 union C2 should always be probability of C1 plus C2, right? This is what one might imagine already. This is very true if the C1 and C2 are mutually exclusive. What does mutually exclusive mean? That they don't have any portion in common, like this section. It has common section, and we saw while we are drawing that this section gets computed twice. So it is essentially we have to remove one of the counting, like double counting. Then the double counting is what the intersection in portion in between them, right? So intuitively one can see this as well easily. Now the proof is also uh, union of non-intersecting series part sets as well. C1 union C2 is essentially C1. Essentially, how they're writing is C1. First of all, they're segregating these portions. So one is first C1 portion is this, and then they're taking the remaining portion as this. This is how the proof for them follows. C1 intersection is everything else intersection C2, and C2 is already they know that C1 intersection C2 plus this portion. So you see this portion is same in between them, right? So C1 and this, so we just have to ensure that we we replace probability. So essentially this would be this minus this. Yeah, that's what they're doing essentially. Essentially P of we have to replace this value from this equation, and the value of this from this equation is P of C2 minus subtract from that this part. Essentially that's what they're doing. It's very similar. The double counting part they're remaining. Ideally it's exactly same, but yeah, one can think of it in this way as well. And I'll just show the extended formula, which is also very similar. So here we only saw two portions, I mean two sets. It might so happen that there are multiple sets. Like for 3, I'll just draw one, so it's understandable visually. Then we can look into the proof itself. Now if we write probability of C1 plus C2 plus C3, we can already see that this portion we this portion at sorry not this portion, this portion we count twice, correct? Because of one coming from P1 and name them. Sorry, I'm just blabbering. Instead, let me write them. So it's C1, C2, C3. It's very understandable. Now what we look into C1 and C2, this portion gets calculated twice, correct? Similarly, this portion also gets calculated twice. This portion also gets calculated twice. Now, one have to also see how many times the middle section gets computed. So essentially, this gets included 3 times, correct? Do you understand? Do we see why? I think we do see why, because one time coming from C1, one time coming from C2, one time coming from C3. All of them have this content. So if we write just this, then it wouldn't suffice. We have to remove the blue parts first. So visually, if we write that C1 intersection C2, this would be this portion. This whole portion we are removing, right? This portion we are removing. Similarly, we have to remove C2 intersection C3. Similarly, we have to remove C3 intersection C1. Now, when we remove from all 3 of them, we don't even include the green one once. So we have to include the green one just once. C1 intersection C2 intersection C3. Essentially, that is what this theorem is. So they can increase it multiple times, and you can see the definition already. Okay. From next day, we'll look into some of the examples, some theorems. I think there's some Bool's theorem and some ring and field concepts we'll need to incorporate. We'll do that. There's no worries. We'll do that. Sure. I think that is it for today. Thank you everyone if anyone's watching. Thank you. Have a great day.